What if I told you there's a kind of logic that doesn't just deal with what is true, but with what could be true, or what must be true? Well, that's modal logic. It's this amazing system for reasoning about possibility and necessity, a whole world of maybes, musts, and what ifs. So you might be wondering, why do we even need this? Well, think about this question for a second. Is the statement, "it might rain tomorrow," true or false, right now? Standard black and white logic has a really hard time with that. It just doesn't fit. It's not a statement about how things are, but how they could be. And that gray area, that's exactly where modal logic shines. Because, let's be honest, our everyday language is absolutely full of this stuff. We talk about what's possible, what we're obligated to do, what we know for sure, what we just believe. Modal logic gives us the formal toolkit to really get a grip on this huge landscape that exists beyond a simple true or false. And this really gets to the heart of the difference. Standard logic is all about facts on the ground. The cat is on the mat. Is that true? Is it false? End of story. But modal logic comes in and adds this whole other layer. It lets us explore statements like, the cat must be on the mat, or, it's possible the cat is on the mat. Okay, so at the absolute core of all of this, the very heart of modal logic, are two fundamental concepts. Pretty much everything else is built on top of these two ideas: necessity and possibility. First up, we've got necessity, and logicians use this little box symbol for it. A statement is necessary if it just has to be true. I mean, there is literally no way for it to be false. The classic example is something like, it is raining or it is not raining. No matter what's happening outside, that statement is always, always true. It's a necessary truth. On the flip side, we have possibility, which gets a diamond symbol. A statement is possible if there's a chance it could be true. Or to put it a little more precisely, if it's not necessarily false. Think about it. We don't have definitive proof that Bigfoot doesn't exist, right? So we can't say the claim, Bigfoot exists, is necessarily false. And if it's not necessarily false, well then, hey, it's possible. And here is where it gets really elegant. These two ideas, necessity and possibility, they aren't totally separate. They actually define each other. Saying that something is necessary, that it must be true, is just a different way of saying that it's not possible for it to be false. That beautiful connection is basically the engine that makes the whole system work. It must be true and it can't be false are two sides of the very same coin. Okay, but this raises a pretty big question, right? How do we actually formalize what possible even means? It sounds a little vague. Well, to solve this, logicians came up with a brilliantly creative and powerful idea, the concept of possible worlds. The official name for this whole framework is Kripke semantics, and it was pioneered by the philosopher Saul Kripke. The main idea is that to figure out if something's true, we shouldn't just look at our own world in isolation. Instead, we should evaluate it across a whole network of related possible worlds. So here's the best way to wrap your head around it. Just imagine a huge web of parallel universes. Something is necessary if it's true not just here, but in every single universe you can get to from our own. And something is possible if it's true in at least one of those other universes. Now that phrase, get to or accessible, that's the secret sauce. For instance, in any possible world that shares our exact laws of physics, traveling faster than light is impossible. So from our world's perspective, those faster-than-light worlds just aren't accessible. But could we imagine a universe with totally different physical laws where it is possible? Sure we can. So the rules of the game, in this case physics, are what determine which worlds are accessible from which other worlds. And this is where modal logic goes from being a neat idea to a ridiculously powerful tool. Because once you realize that you can change those rules of accessibility, you unlock its true potential. It's not just one single system of logic, it's a whole family of logics. Each one has its own unique flavor, depending on what possible means in that particular context. So, take a famous unsolved problem in math, Goldbach's conjecture. Nobody has proven it true or false yet, so based on everything we know right now, it's possible that it's true, and it's also possible that it's false. Either outcome is on the table, which leads us right into our first flavor. This is what we call epistemic modality. It's the logic of knowledge. In this system, possible just means it's consistent with everything I know, and necessary means it's certain based on the evidence. You can think of it as the logic a detective uses to solve a crime.
And this is a perfect way to see how the same word, like must, can mean totally different things. A detective saying Agatha must be the murderer is making an epistemic claim. The evidence leaves no other possibility. But a judge saying Agatha must go to jail, well, that's a completely different kind of must, isn't it? That's not about evidence anymore. It's about obligation.
And that brings us to our next flavor, deontic modality. This is the logic of what ought to be. It's all about rules, duties, permissions, what's morally or legally required. In this system, an accessible world is an ideal world where all the obligations are actually met. Okay, let's try a different spin now. Think about this statement for a moment. It just feels right, doesn't it? The past is fixed. What's happened has happened. You can't change it. This powerful intuition hints at yet another kind of modality. This is temporal modality, the logic of time itself. Here, the past is treated as a single, fixed path. It's necessary. The future, on the other hand, is a branching tree of possibilities. This kind of logic gives us special operators to reason about what will be the case or has always been the case, letting us talk with real precision about past certainties and future potentials. So we have a logic for knowledge, a logic for ethics, a logic for time, and this is not just some abstract game for philosophers. All these different flavors of modal logic have some incredibly important real-world applications. Whoa. Okay, don't worry about trying to read every single box and arrow on this thing. The point is the big picture. This is a map of a huge, interconnected landscape of logical systems. Each different system is just built by tweaking the rules a little bit. By adding or removing simple rules, logicians can literally design the perfect logical tool to model any specific kind of reasoning they need. And these tools are used for really critical stuff. In artificial intelligence, modal logic helps a robot reason about what it knows for sure versus what it only thinks is possible. In computer science, it's used to formally prove that a program, say in a pacemaker or an airplane's flight controls, can never enter a dangerous state. It's also a foundational tool in modern philosophy, linguistics, legal theory, and even game theory. So I'll leave you with a final thought that kind of ties all of this together. We all agree the past is fixed, it's necessary, and we also know that everything that happens in the future will eventually become part of the past. So, does that mean the future is already written? Are all future events in some sense already necessary? It's a classic philosophical puzzle, and it's exactly the kind of question where modal logic helps us sharpen how we think and how we ask.